And next step from there
hard to get to
becomes Hamiltonian mechanics. That's even another step farther. That
I haven't even gotten there yet.
It mainly is, again, I mean, if we are familiar with the Hamiltonian from quantum mechanics, or, I mean, technically you shouldn't be doing quantum before this, but we did, so it's funny.
Why not, though? Like, why? It's two different ball games.
I guess you're right. I guess you're right, but it's just interesting to see that, well, the Hamiltonian from Hamiltonian mechanics and classical mechanics is representing the Hamiltonian of the system, which is what we see in quantum mechanics. So in quantum mechanics, we're told that the Hamiltonian is kind of like an evolutionary operator. It's telling you how much energy a system has. And that's basically what the similar thing in Hamiltonian mechanics is in classical mechanics. However, the advantage, and again, we're not going to get into this, neither do I really understand the exact implications and the real depth of it, but the biggest advantage of, well, Lagrangian mechanics versus, let's say, Hamiltonian mechanics is that, well, Hamiltonians, again, they commute. They work with quantum operators. They work with things that we're used to. So the Hamiltonian, I mean, a more scientific way of saying it is that the Hamiltonian can be quantized, but the Lagrangian cannot. Like, cannot always be quantized. So what is usually done is first converted to a Hamiltonian via a transformation, and then you do all this analysis. So it's pretty cool why we do it and like these different steps. But you also might be asking yourself now, well, okay, I get it that, you know, it's a little hard. They're hard steps, but like, what are these steps for? Like, we're understanding that, okay, F equals ma. But like, what am I learning about the system from this particular equation, right? And that comes from equations of motion. Right, I mean, we can kind of dabble into that because I think that is the fundamental concept of understanding what's actually happening in a system.
Because they don't tell you that in high school.
Not at all.
What they tell you is, okay, so F equals ma. Once you have the acceleration, then you find like the initial velocity, the initial position, and then you can plot out its motion or whatever. But it turns out motion is a lot more complicated than that, and so we have these things called equations of motion, but they don't explicitly tell you like where the particle is and where it's going. It just tells you the rule that it must follow, no matter where it is, and no matter, or I guess it could depend on where it is, but you know, if you, like I'm saying, no matter where it is, as in you can say it's here and it will follow the rule that the equation of motion gives you. So yeah, equations of motion, they come from F equals ma, at least in the beginning, when you learn about equations of motion. And the reason is because F equals ma, as spoken about in another episode, are differential equations. Second derivative of position with respect to time is acceleration. Okay? And so it's pretty straightforward. Well, you know, the thing about differential equations is that there is no general solution to a differential equation. There are ways to solve specific differential equations. But if you were to give me a function of, let's say, time and position and velocity, acceleration, ... there's no general solution.
Like, there's no general way to solve, you mean? Or
okay.
No,
like general solution. I'm saying,
I guess, yeah, you're right. I think we did
like
mention this on the podcast.
If you just have like some random amalgamation of terms together, and you say that's equal to 0, like there's no way for you can solve it numerically, but that's not really an analytical solution that we love. But there are specific equations. For example, linear equations, which we love very much, because F equals ma for easy situations is usually a linear thing, or you can even approximate it as a linear situation. So for example, I think the biggest example that you revisit time and again in university is simple harmonic motion. Just a mass on a spring. The reason why it's so important is because you can learn about, you know, how the equation of motion changes and how to deal with those changes. And also, not even just that, let's say you have just a mass on a spring, and then we say, okay, what if we consider the air friction? Then it'll slow down. The oscillations will get smaller and smaller. Well, let's see how that term fits into our equation of motion. And then let's see the things that arise from that. Also, then we ask, what else can we put in there? Well, what if we have a driving force? So somebody is forcing the spring to go at a certain frequency. And then what comes out of there? Well, you get things like resonance. Mm-hmm. You get things like destructive interference, where, you know, the spring could just, the mass could not move at all, even though there's, you know, something counterbalancing or counteracting it. It just still won't move. And then we're definitely going to talk about coupled oscillators in a little bit.